Okay, 15A. So, a cyclist, Laura, is travelling in a straight line on a horizontal road at a constant speed of 25 kilometers per hour. A second cyclist, Jason, is travelling closely and directly behind Laura. He is also travelling at a constant speed of 25 kilometers per hour. The driving force applied by Jason is likely to be less than the driving force applied by Laura. Explain why. So, if Jason is travelling directly behind Laura, then he is going to be in her slipstream, which means that he experiences a less wind resistance. So, anything like that, and he would be fine. Okay, then for B part 1, Jason has a problem and stops, but Laura carries on at the same constant speed. Laura sees an accident 40 meters ahead, so she stops pedaling and applies the brakes. She experiences a total resistance force of 40 newtons. Laura and her cycle have a combined mass of 64 kilograms. We want to determine whether Laura stops before reaching the accident. Fully justify your answer. Okay then, so let's pull out the important information and see what we can do with it. So we know her initial velocity, u, is 25 kilometers per hour. We know that her final velocity, well, we want her to stop, so her final velocity is 0 kilometers or whatever, meters per second. So we'll just leave that as 0 for a second. We know that her mass, actually, no, we know her displacement from the accident is 40 meters. Now, at this point, this then tells us we want her velocities in meters per second. So, to turn her initial velocity into meters per second, well, 25 kilometers is 25,000 meters, and there are 60 times 60 seconds in an hour, which is 3,600 seconds. So that's going to give us 6.94 meters per second. Cool. Okay. Now we also know her mass is 64 kilograms. And we also know her acceleration. No, we don't. We know her force, or the force that she experiences, is a resistance force of 40 newtons. Okay, so from that, we can actually work out the acceleration that she experiences when she applies the brakes. So, force is mass times acceleration. So, acceleration is force divided by mass. Now, when she applies the brakes, she is going to decelerate. So we're going to say then this is minus 40 over 64. Now that's going to give us minus 0.625 meters per second squared. Okay, so now that we know our acceleration and we know displacement and initial and final velocities, it's now a job for this guy. So we get, and now remember we're looking for S here, we want to know how much further she keeps moving. So we get 0 squared is equal to 6.94 squared, add 2 times minus 0.625 times S. Now, if we add the S term to both sides, 2 times minus 0.625 is minus 1.25. So if we add 1.25s to both sides, we get 1.25s is 6.94 squared. So S is 6.94 squared over 1.25. Now to 3 sig figs, that's going to give us 38.6 meters. Now 38.6 meters is less than the 40 meters that she is from the accident. So she stops in time. Cool. Okay, then for the final part, we want to state one assumption that we have made that could affect our answer to part 1. So, I guess the first one that springs to my mind is we have assumed a constant resistance force of 40 newtons, which isn't going to be the case. As the speed decreases, so too will the resistance force. So that will make a difference. It would probably mean we are actually going to travel further than we worked out. So there's that. And the other one, I guess, would be that we've assumed Laura applies the brakes as soon as she sees the accident. In reality, there's going to be a tiny little bit of delay between her seeing the accident and her applying the brakes, her reaction time. So in her reaction time, she is going to also travel a little bit of distance, so that too might also affect our answer. Cool.